Welcome to a new lesson of the Haskell course. In this one, we're going to cover small tips and tricks and then the final project of the section. For tips and tricks, we're going to cover REPL, Hackage, Hoogle, how to use undefined, and type holes. We already saw how to use the REPL, both using GHCI and Cabal REPL. When you're working on a project, remember that you always have the REPL available for you. And if you enter the REPL using Cabal REPL, you can also import and explore modules you download using Hackage. For example, in this project, I have the random library as a dependency. If I enter the REPL using GHCI, and I try to import the random library, I'm not allowed because GHCI has no access to my Cabal libraries. So if I exit this and I enter using Cabal REPL, now I can import system dot, and if I tap for completion, I get all the system dot something modules that I can import. And if you can see, there's right here system dot random. And now that I imported it, I could, for example, check the type signature of random range IO. And I can interactively test the library. For example, give me a random number between 50 and 70 integers. And if I correctly write this, okay, that's what I want, so I can use the library. And of course, it's not just other libraries. You can also check your own functions that you wrote. So if you can see right here, I have this tic-tac-toe module. So if I import tic-tac-toe, now I have access to all the code inside that module, and I can test my functions. For example, I can check the type of the game loop that I'm not going to show because you have to do it in the project. And that's it. As you can see, you can interactively check your own functions and other library functions. But for other libraries, usually it's just better to use Hackage. Hackage, as we already saw in a previous lesson, is the Haskell Community's central package archive. At the time of the recording of this video, there are over 16,000 Haskell packages available in Hackage. We already saw how you can use it with Cabal to add libraries to your project, but let's take a quick look at the actual website and how to use it. So, for example, we want to build a web server. So we can write here in the search prompt, let's zoom in, web. We have access to advanced options, but this is enough. We can filter for maintainers, the last update, ratings, and downloads. This is, I think, weekly downloads. So if we click here, there you go. We filter the libraries for most downloaded to less download. Here we have conversion between math format. That's not what we're looking for. We have Warp, which is a lightweight web server. We have Yesod Core. We have a bunch of other libraries that we can choose from. And now, for example, let's explore the Y library, Web Application Interface. We have the name of the package here. This is what you write in Cabal. We have a short description with a README. We have the modules of the package, how we can download it. We don't really need this because we usually use Cabal or Stack. Who's the maintainer, all the versions. If we click in any of these links, we will get the same page we are right now, but for the version at that point in time. We have the changelog, the dependencies. Same as with other languages, the less dependencies, the better. This is really just a few dependencies, so that's amazing. Other information, but What we really care about is downloads, a bunch of downloads. The rating is not usually a good indicative because there's no much voting here. So the actual votes is the usage, and the usage is huge. And of course, we have the source repo that we can open and check if it's been updated frequently and if it's up to date with the latest GHC, etc., etc. Of course, once we choose it, we want to explore how we can work with it. And for that, we can click at the modules. One really cool thing that we have in Haskell is that we can auto-generate documentation because we have the types and the usage, and we can easily add small comments that then were going to be part of the documentation. So whenever you want to work with a module, you just click on the module. You get a short outline that you can click through, and then the explanation and the documentation of all the types, type classes, and details, and even examples on how to use these libraries. So as you can see, this is easier to read than the REPL, but it's not interactive and you cannot check with the values you're actually using in your code. So both are useful in their own way. Next, we have Hoogle. Hoogle allows you to search a commonly used subset of Haskell libraries by their function name or by approximate type signature. This is useful in several scenarios. For example, imagine that you want to print a string to the console, but you have no idea of which function could do that, or you know that there is a function, but you don't recall the name of the function. So here you can just write the type signature the function you want should have. So we have to give it a string, and it has to give us back an IO of unit because it prints to the console, but it doesn't return anything. So Hoogle give us back correctly the putString function and putString-like function that are both in the base library and in other libraries. And if we click on the function, we get redirected into the explanation provided by Hackage. Another useful use case will be if you know the name of the function but totally forgot about the package where it comes from. For example, if you want to use the try function that we saw the last lesson, you can write try and you get that there's a try function in the base library, there's a try function in parsecs, exceptions, etc. And the one that is in the base library is actually the one that we learned in the previous lesson. So if we click on this, we get the explanation of how try works and an example of how to use it. And of course, if we scroll to the top, we see that it's part of the base library and it's inside the control.exception module. And finally, something that it's a bit more difficult, but it still works, is to search for concepts. For example, if you want to work with natural numbers and you want to see if there is a module named natural or nat numbers, something like that, you can try search for it. And here we see that there's a module called numeric natural in base. And for example, if you want to search for something in the web, like web sockets, we see that there is a package that you can install called WebSockets. And if we click here, we can explore it, etc. So as you can see, Hoogle is really useful to find functions, packages, modules, and documentation. Next, we have the undefined value. If we search in Hoogle for undefined, it's in the base library. And here it says a special case of error. We saw this in the previous lesson. Error just stops the execution and displays an error message. So, if undefined is just a special case of error, it's a value that as soon as you evaluate it, it halts the program. Of course, as we saw in the handling errors lesson, we don't like runtime errors. So why I'm sharing this as a tip? Well, in practice, undefined is a great tool to keep the type checker assisting you while working on a half-baked code. Let's see how. Let's go to the lesson 16, close this. So, let's say we want to create a function that reads a CSV file, transforms the content into JSON format, and then writes a new file with the content, but also returns the JSON at the end. First, we create new type wrappers for both the CSV and JSON values. This will make sure we don't mix CSV and JSON values by accident, and that the compiler will provide more specific hints, even if the underlying value in both cases is just a string. Then, because we don't want our program to crash if, for some reason, the reading and writing of files or their conversion fail, we will catch the errors and return an either type. Either there's an error and I will provide a string to showcase in the UI, or I will provide the JSON value. Okay, now we can start implementing the function. Because we are just starting and we don't have a clear idea of how we want to implement this, we will go step by step. I'm going to behave naively to showcase the usefulness of undefined. Let's start by printing a message to the console and reading the CSV file. Because we are in I/O, we can start a do block. And here we can say put string line, reading CSV file, I want to read the file, and I want to save the raw content in a binding. And now I have a type check error. Let's see what it says. The last statement in a do block must be an expression, and we are not providing an expression. This is technically correct, but not the error we will expect, especially because there's an even more fundamental error that the type checker is not telling us about because it's stuck in this one. We could be making mistakes like writing gibberish here, and the compiler won't tell us anything useful. This is one of the cases when undefined is really handy. If we add an undefined as the last statement in the do block, like this, we're essentially telling the type checker, trust me bro, from here on everything is fine, don't sweat it. So the type checker, assuming everything is fine there, will continue to analyze the rest of our code and give us useful information. In this case, we got 3 different errors that will help us realize that one line is gibberish and that we didn't specify the arguments of our function. So we have to do that. We have to provide the file path. And now that that's fixed, we can go to the read file function and say, oh my god, we also forgot to pass the file path to the read file function. So let's pass the file path. And now that we have no type errors, we can be reasonably certain that everything up until undefined is okay. Another use of undefined is to check the behaviors during development. For example, we still have to parse the contents to CSV, that could fail, then convert them into JSON, that could also fail, and finally we have to write the new file. And on top of that, we have to do the error handling. Instead of writing the whole thing and checking that everything works at the end, we can check the values in intermediate steps by running the code with the undefined there. For example, we can check the contents of the file we are reading by printing them before the undefined. So we can print there. And now we open a REPL. And we can do, for example, CSV. And we have a changelog file right here. So we can do. And as you can see, we get the contents of the file printed here, and then our program crashes. So we know that up until here, everything is fine. Because undefined is just a fancy error, if we run the program, we'll get a runtime error. Of course, by the time you are done writing the code, there has to be no undefined left. This is just a tool for your convenience during a development session. You could get fired if you ship an undefined value to production. But we don't care at this point because we are mid development and we just want to check if everything we coded so far is fine. Finally, one last good use case for undefined is to use it as an implementation to do. For example, let's say we keep going with our function. Let's close this. As we said before, we have to parse the CSV, so let CSV, we apply the parse CSV function to the raw CSV to get the final CSV value. And at this point, we have an error because there's no parse CSV, and that's because we didn't implement it yet. One option will be to implement parse CSV right away. That will be fine. But what if halfway through implementing it, you realize you need to implement another function and another one, etc., etc. This specific case wouldn't be that complicated, but you can see how in more complex cases, by the time you finish implementing all the internal functions, you lost track of what you had in mind for the original one. So, if you have a rough idea of the overall structure of the function you are implementing right now, you can defer implementing the internal functions by creating the internal function signatures and setting the actual implementation of it as undefined, like this. We can write parse CSV, and we want parse CSV to take a string and return a CSV value. And instead of actually implementing it, I'm just marking it as undefined. So now the error is gone. We have a function that actually shows the real value that we're going to get. And we have the correct value for the CSV binding. And of course, we can keep doing this. For example, we can define the CSV to JSON function that takes a CSV and returns a JSON. And trust me, I'm going to implement it sometime in the future. Now we can come here and actually use the function. CSV to JSON, if we want to pass the raw CSV file, we're going to get an error that is not the actual type. So we have type safety even if we don't have the function. So we have the correct CSV. And now, because we know this is a value of JSON type and JSON is just a new type wrapper around string, we can pattern match to extract the actual string and write a new file called newfile.json with the JSON contents. And now each undefined is like a to-do item. The first one, this one, indicates that you still have to add error handling, because if we delete it, the error we get is that we couldn't match the type unit with either string JSON. And the other two indicate that you still have to implement those two functions. So you essentially split the work into three, and you can start tackling each to-dos one by one. Now, let's move to the final tip of the lesson. Type holes. Type holes are a feature of GHC specifically designed to help you figure out what code to write when you are unsure. It works like this. I have the boilerplate right here. Let's say you're implementing a function that parses a list of strings into valid emails. The type email is just a type wrapper around a string to provide extra safety. And the parse emails function has to first make sure the user input is a valid email by checking that it contains the @sign. And then it has to normalize it by converting all characters into lowercase. Okay, so let's start easy by just straight up converting a string into email without doing anything else. If we change the undefined to an underscore, we get a pretty interesting error. This is what type holes brings to the table in Haskell. By putting an underscore in our unfinished code, we ask the type checker for hints about what could be done there. And the type checker brings all the information it can. First, it tells us what's the type of the hole. So we found a hole, which is this one. This hole doesn't have a name, but we could add a name if we want, A, for example, or X. And it will find a hole X, so you can have multiple holes at the same time. So we found a hole that is of type list of string to email. It makes sense because we didn't do anything, so we have to implement the whole parse email function, and that's the type of the parse emails function. But also gives you the place of where it is. Usually you already know where it is, so that you could skip that if you want. But it gives you relevant bindings. In this case, it's just parse emails. But if you have a where clause or let bindings, all the bindings inside the parse email function will be shown here as well. More interestingly, we have valid holes fits. In this case, the type checker provides values that perfectly fit the type of our hole. We have the same function, so of course, if we recursively call the same function, the type will be okay, but we will have infinite recursion. And we have other value that we don't know what it does yet, so we won't talk about it just now. But on top of that, it realizes that there are other things that don't have the exact type that we need, but they could move us closer to the type we really need. And these are the refinement holes. As you can see, we have map with an underscore, meaning that if you replace the underscore with map underscore, you will be one step closer into the type you need. And we have the same with a bunch of other functions. But in this case, we know that we have to map over the list of strings. So we take the first refinement hole suggestion and write map. Let's see, write map and underscore. Now we check the hole again, and we get a whole set of new information. And if we look at the valid hole fit, let's see, what is it? Valid hole fits includes email. The email constructor is there. And we know that if we wrap a string with the email value constructor, we get something of type email, which is exactly what we set out to do. So we accept the suggestion and replace the underscore with email constructor. So let's email. And voila, our function compiles. Now our function correctly transforms a list of strings to a list of emails, what we set out to do as the first step. But we are far from finished here. We said that we wanted to filter emails that didn't contain the @character. So let's do that. Of course, we know about the filter function, and we want to filter the strings before constructing the emails. So we are going to compose this function with the filter function, and then we are going to ask the type checker for hints. Let's see. So, okay, we find a hole that goes string to bool. So we have to provide a predicate. But if we go through the type hole, we don't see anything that could be useful here. And at the end, we have this little message that says some refinement hole fits are suppressed. We can use fmax refinement hole fix n or no max refinement hole fits to increase or reduce this list. we have this message because the type checker found more suggestions than the maximum allowed by default. One thing we could do to get more hints is to disable this maximum allowed by writing a pragma with the flag indicated right here. So let's go to the top and write the pragma. We're going to provide an options GHC pragma, and the options we can actually copy and paste from here. No max refinement hold fix. Fits. There you go. So if we now save and hover again, we see that there are more suggestions than before. And one of the refinement suggestions is the lm function. We already know the lm function. We used it before. We know that lm is a predicate that returns true if the element is inside the list, which is exactly what we need. So we substitute the underscore with lm underscore as suggested here and keep going. So lm underscore, and we hover again. Now we found a hole of type character. This time is pretty obvious. We don't even need the suggestion. We know that we need to provide a character to check if it's part of the string, and we already know which character was because it's part of the requirement. So we provide the add character. Done with the filtering. Now let's normalize the emails, because it makes sense to normalize the string before wrapping them with the email constructor. We will do the same as we do with the filter and compose a type hole. In this case, we want to compose the function that we map over the filter strings. So we're going to use the parentheses and we're going to compose a type hole. If we hover over this, we get that the hole is a string to string, relevant bindings choose parse emails, and valid holes, there's a couple of them, there's quite a few, and then refinement holes, there's a huge list. If we slowly go through the list, we can see that reverse, cycle, init, tail, these don't do what we need, fail, read, and take while, drop, filter, we don't need all these. So after looking at this for a bit, there's one refinement hole that looks clearly as the best option, which is the map function. We have a string that we want to convert to lowercase. A string is just a list of characters. So maybe we can go through every character and return the lowercase version one by one. So we accept the suggestion and replace the underscore with map underscore. And if we hover, okay, we need a function that goes from character to character. And if we take a look at the functions provided, none of them look particularly useful. But we have one more ace up our sleeves: imports. We get these suggestions because this is what we have available in our environment. So if we want more suggestions, we can add more to our environment. In this case, we want to work with characters. So a good initial idea will be to import a module that is full of functions to work with characters. We already know that the data.char module is the prime candidate for this. So let's import it and see what extra options we get. So let's go to the top and say import data.char. And now if we go to the bottom and hover again, behold, between the valid hole suggestions, there is a function that perfectly fits our hole with the name too lower. It looks too enticing to ignore, so let's accept the suggestion. If we read the documentation, says that it converts a letter to the corresponding lowercase letter, if any. Any other character is returned unchanged. Perfect, exactly what we needed. So if we use it, it compiles. And it looks like we finished implementing all the functionality we wanted. So let's test the function. We can use the REPL, or for convenience, we can use a really cool functionality that allows us to evaluate the functions inside the files. So if we do and we write parse emails, and now we have to provide emails. Oh, now let's add an email with capital letters. And finally, let's add a string that is not a valid email. So, according to our specifications, only the first and the second should be part of the final list because they contain the @ sign, and both should be in lowercase. So this one will be untouched and this one will be all lowercase. Both will be wrapped in the email constructor to signal that this is a valid email. So let's evaluate. And we get that there's no instance to show email because we have to derive it. And if we now refresh, we get the answer that we needed. Notice that I did very little work because the type host slowly guided me through everything I needed to do. I just took key decisions as to the direction that I want to go through, but that direction was gently provided by the type checker. As you can see, type hosts can be really useful, especially when you're working with many polymorphic values or nested structures. And that was the final tip. So let's talk about the section's final project. Let's review what significant things we did in this course so far, besides learning Haskell. In Lessons 9 homework, you build a closed maze and an open maze solver. We call the open maze forest. In the Lessons 11's homework, you had the opportunity to build a program that prints a tree-like graph representing a folder structure. In Lesson 14, we build a CLI game in which the user tries to escape from a forest before it runs out of stamina. And in the homework of that lesson, you added a battle system to fight golems while trying to escape. And finally, in Lesson 15's homework, you went through and understood the code of a CLI program that you can use to manage your to-do list. And on top of that, you added error handling to fix the bugs I purposely hid in the code. By now, you have a couple of programs under your belt. And in every step of the way, we introduced new concepts and I provided you with thorough guidance about what to take into account and how to approach those challenges. Now it's time for you to build something by yourself. Here are the requirements. You have to build a tic-tac-toe game. It has to be a CLI executable with its business logic implemented as a library. There has to be a single player and a multiplayer mode. The single player you have to play against the machine, and the machine has to randomly pick the next movement. The board has to be nicely printed in the console, and finally, you can use whatever library you want. However, I'm going to provide the solution, and I will only use the random library and the Haskell features explained up until now. So, if you are tempted to use more advanced features, you are likely overcomplicating it. The only way to learn how to code is by coding. So, make sure to do the project, and I will see you in the next one.